one camera and another camera love each other very much.
They make a baby camera.
And they are smaller. If you notice that cameras have gotten smaller, it's because babies have just gotten smaller.
The only problem with this camera is that because of these lights, it makes me look like my hair's a little thin on top. Do you notice that?
No, it just looks like you have really shiny hair.
I know, I need makeup. Makeup! Okay. All right, forget the cameras there. So a couple quick things. I've got some good news and bad news. Well, it's probably good and bad news. I have been called out of town. I've got to leave tomorrow. I won't be back until Saturday. That's the good or bad news. The other good or bad news is that's okay because we have an exam. So I had planned on giving you the exam on Thursday. However, I'm going to make it a take-home exam, and I thought I'd just give it to you. I'm going to put it up on Canvas today. And you have until next Tuesday to complete it. Okay? But it will be done at 10:30 a.m. on Tuesday in this class. No late, no nothing. Okay.
If for something crazy,
then you need to get it to my box before then,
right.
Sometime between now and Tuesday.
Could we just submit it through Canvas? Or?
I don't really want, no. I think I'd like the hard copy because unless you've got a really nice scanner and it looks professionally done, like PDF, yeah.
What if somebody steals our test answers and publishes it in a professional journal under their name?
I am planning on doing that.
Oh.
Yes. Yes, I am planning on doing that.
What am I going to do?
I'm just making sure this is going. Hello. Okay. Yeah, we're good. And you are not visible, so you don't have to worry about it. So Mike, I was just saying that exam, I'm out of town for the rest of the week. I've been called out at the last minute. So exam, I'm going to put it on Canvas today.
Where are you going?
Due next Tuesday. I've got to go see my family up in Rochester, Minnesota. No, it's not science stuff. It's family stuff. Got to go deal with family. But,
Very excited about that.
well, you know, there are better circumstances to deal with family. But they'll be looking forward to seeing them. Okay, so any questions about the exam? You want to know anything about it?
Yeah, how many questions?
All right. So I will tell you this because it says it on the exam. This is an exam. I'm trying something new. It's a take-home exam. You can use any materials at your disposal.
Including?
Anything at your disposal except other people. You cannot crowdsource this on Facebook, right? You cannot talk to each other. You cannot hand in the same exam, right? There are a bunch of rules on the exam. You can read through it. But I think the critical piece is there are a bunch of questions of all different point values. And the way the scoring is going to go is you're going to get 20 points for the awesomeness of your presentation, right? The quality of your professionally prepared exam.
So if we turn the stereoscopic 3D on a DVD,
you're going to get all 20 points. Yeah. Yeah. I mean, yeah. Sure. If you want to make a 3D video documentary of everything on this exam, that's awesome. Okay. The second set of 20 points, you will get for the completeness and accuracy of your work. So even and by accuracy, I don't mean the correct answer. I mean that your thought process is documented, and your logic is correct, and solved consistently. You might be wrong, but at least you have, and you've stated all your assumptions, and you've defined all your variables, and you've got it all laid out that I can follow the rational argument of how you got to it. You could be completely wrong, but you'll get 20 points for doing that. And then finally, there's 60 points. The last 60 points will be collected from whatever questions you choose to answer.
How many questions do you have to choose?
You have to choose up to 60 points. Some of the questions are worth 30 points. Some of them are worth 15. If you can only get the maximum of, well, it's 105 points because I did put one extra credit question on there. But the maximum is 105 points. However, if you do all the questions, I will grade them all and give you the best possible score. So if you wind up getting 190 points on the exam, you get 105, but that's the maximum.
But you also get the joy of having solved all those problems.
Right.
So if you get the extra credit question wrong, but you still end up with 190 for all the rest of the problems, would you still?
Then your max is 100. Okay. Yeah. Yeah. So your max is 100 unless you answer that 5-point extra credit. So that means I kind of want you to answer that question. So I figured, but so you can do a bunch of things. You can do. So I believe I tried to make it so that you could Yeah, I think there's 5 questions, 4 worth 15 points and 1 worth 30. So if you do the big 30-point problem, you only have to do 2 other problems. But if you don't want to tackle the big 30-point problem because you're like, whoo, then you do the other 4 problems.
That doesn't add up to 100.
No, it's 60 plus 20 plus 20.
Oh.
Yeah, because so we have collective marks.
You're set.
I thought the
Yeah.
100 mark was for the points.
No. So yeah, so 105 total
Okay.
over the whole thing. But I'd like people to get credit for doing quality work even if they're wrong. Because frankly, I did excellent quality work in my PhD dissertation and it's wrong. But I still got really good marks on my PhD dissertation. Turns out I was wrong. So it's all about the process, and it should be fun. I picked some problems that are kind of very similar to what we're doing in here, also some problems where you get to kind of bust out and use what you've learned on something that may not have a correct answer. And this is why it's very important for you to document what you're doing, right? Write down your thought process, all that kind of stuff. Now you can use anything you want. Obviously, if you've copied your solution off of Wikipedia, I'm pretty sure I will know that. So don't do that, right? Okay, questions about the exam though? I expect it to be fun. And you have a week to do it. Now you do still have a homework assignment due Thursday as well.
You just turn it in under your...
Yeah, yes, absolutely turn it in Thursday by midnight because I will know. Yes, because I've set up this video camera to look under my door and email me the picture of the pile of assignments Thursday at midnight. And if they're not there, then I will know.
Fail the course.
Yes, fail the course. Okay. So no other questions?
Sustained.
Sustained?
Yes.
Objection. Overruled. Okay. All right, so let's get back. We were talking about the radiative transfer and how this can be written down in a mathematical way so we can discuss how stuff in bulk gets transferred, how light in bulk gets transferred through material. Now this is really exciting because we're just entering a new inversion.
Yeah.
So we got all the crud in the air. This is a perfect radiative transfer problem, right? Because you have the light source, which is the sun. Because we're filming this, I'm elevating my diagrams, okay? This is the sun. You've got crud.
Crud looks like we're going to see absorption line.
You're going to see at least in the broadband spectrum, you're going to see a reduction in the amount of light coming through. If there is a spectral component to this, like it's a particular type of a material, yes, you will get absorption lines. But you get light coming in like this, some of it gets absorbed, and you get less light coming out the other side. So what we want to talk about today are the bulk properties, not the spectroscopic properties, but the bulk properties. And really what we're trying to get to is why can't you see through this crud? Right? At what point can you start to measure? If I could measure how far I could see out there, right? Could I tell something about the crud that I'm seeing through? Is there something I could deduce about the nature of crud? Because if you think about it, what we're doing out here by looking towards the mountain and not seeing it is exactly the same as looking through the Milky Way galaxy and not seeing the stars behind it. So if we can look through the Milky Way galaxy and see how far we can peer into the Milky Way and learn something about the radiative transfer of material of light through that material, we can learn something about the material, right? Then we've learned something about stuff we can't bring to Earth to study. So that's why we're interested in this. And it turns out you can do this exact same thing out here. If you want to know what all that crud is, I mean, how do they know the particulate count and the nitrous oxide and all that stuff, sulfur dioxide in there? They basically do what we're talking about. They do radiative transfer through the gunk to figure this out. Yes. Yeah. Although it's mostly hydrogen and helium crud. But it does have dust and other various stuff in it. But yeah, I mean, it's pretty much just, all this stuff in the air is just, you know, just various stuff. We'd like to know what it is, so we can do this kind of radiative transfer. The other reason this becomes important, and the reason we're going to talk about it in this class, is that by using radiative transfer, you can figure out how much energy is being deposited by the light, right? And this becomes important in, say, studying climates of planets. Because if you've got radiation coming through a transparent atmosphere that's then re-radiated by the Earth and then gets absorbed by the atmosphere because the atmosphere absorbs infrared radiation through CO2, you can start to model the effects of greenhouse gases. We can figure out why Venus has a runaway greenhouse. We can figure out why we're contributing to global climate change. Right? So this radiative transfer stuff is pretty important. The other reason we like radiative transfer is because it allows you to study the structure of stars. Because again, you've got a source of radiation at the center, that's the nuclear fusion, and you've got all this crud in between you and the source of radiation, and you can figure out the interior structure of the sun by studying the spectrum of the light that comes out of it through radiative transfer. Okay? All right, so we had written down an equation for radiative transfer where we had gone through some of the analysis to get properties of this thing, and we wrote down this equation here, that the intensity as a function of position x, as we're walking along this way, this is our x-axis, is equal to whatever intensity you started with times e to the minus n sigma x, where n is the number density per cubic meter, and sigma is the cross section. Cross section. And what are the units of sigma? This is per meter squared. This has to be meters, or per meter cubed. This has to be per meter, or this has to be meters squared because we multiply it by meters, and we get a unitless number in the exponent. Okay. So what does that look like? That's just a exponential. And where this drops off by 1 over e is going to tell you something about the properties here. Right? And that's the transition where we get where n sigma x becomes 1 is the transition between something known as optically thin and optically thick. And the way I try to think about it is kind of about the area where, you know, if you're looking into this crud in the atmosphere, when does the amount of light you're getting from the mountain drop off by 1 over e? Right? That's the distance. You can think about the physical distance. So if you could measure that physical distance and then you measure the intensity, you could tell what n sigma x was. Those quantities multiplied together.
What are the units of intensity?
The units of intensity. Ah, thanks. Yeah, the units of intensity are, depending on what we're doing, right, they are usually joules per second per meter squared per sterradian. Yeah, that might be. Who's heard of a sterradian before?
Nuclear physics.
Nuclear physics. Okay, so sterradian is a three-dimensional radiance. Yeah. Well, two-dimensional, I guess, because it's the angle this way and the angle this way. So 4 pi sterradians is the whole deal, right? Is that right? 4 pi, 2 pi, 4 pi sterradians is the whole deal. So that's why when we integrate the intensity we're getting, we're going to do this in just a minute here. When we integrate the intensity we're getting, say in a telescope, we have to integrate over, oh, well, I forgot, this is also per wavelength. Depending on what we're talking about, because we have to integrate over the wavelength we're looking. We have to integrate over the size of our telescope. That tells us how many sterradians we're looking at. We have to integrate over the area of our telescope, because that's how much light we're absorbing. And then you have to integrate over the amount of time you've observed, and then you can get joules, the amount of energy you received on your instrument. Okay, so it's broken up by all those pieces.
So the nu or the lambda is included as part of the unit?
Yes. Yeah. So this is. So I should say. Well, let's do this. Let's say. Hertz. How about that? So that's by frequency. You would think, but it doesn't, because it's not. It does cancel out seconds, but it's a frequency.
Okay.
So that's why we leave the seconds out here. This is seconds of time. This is hertz of frequency.
Oh.
So the way you read this is you say the amount of energy received per second per square meter per sterradian per hertz. Yes. Yeah.
Is there an actual unit that we give this, like a name?
Well, we call it flux, or yeah.
But there's nothing like a candela or anything?
No, it depends on. So in radio astronomy, it's called a Jansky.
Chance?
Yes. Yeah, and they just named it after Jansky, who was a famous radio astronomer. But it's only. But that's a very specific. It's like 10 to the minus 24 joules per second per square meter per steradian per hertz.
So it's like an angstrom. It's not really.
Yeah, it doesn't have a named unit. So, and frankly, most of the time, when you're looking at a source, you kind of have an assumption of what wavelength, like you see with your eyes, right? So if we were talking about the intensity of these lights, we would already assume we were integrating over the visible spectrum. So when we measure the intensity with a meter, we just leave that out, because we're automatically, if the meter has the same spectral response as your eye, that's already taken into account. Okay, so I want to put this in terms of the opacity, right? So we want to figure out how opaque the material is. And so in order to do that, I want to define this variable called tau as n sigma x. And n, you should know, really n is a function of x, because the material could vary. You could have clumpiness. We often don't worry about that in astronomy because we can only see in one direction, so we're really just getting the integrated stuff along the path, and we don't know the distribution along the path, so we just say, well, it's whatever the average number density is. Yeah?
You said n is the number of what?
The number of whatever things are interacting. So it could be atoms, right? It could be molecules. Yeah, whatever particles are in there. It could be photons, right? So you just have a gas of particles, right? So I should say number of particles. Okay. And so this tau here, I can rewrite this guy just then as I of x, or let's say I of tau, is just equal to I naught e to the minus tau. And tau of 1 is when we have reached a path length in the material that is equal to the mean free path in the material. Can everybody remind me what the mean free path is?
That is the path the particle takes on average cloud around it.
Yeah, so it's the average distance you travel before you hit the particle, right? So I've got a particle here, particle here, particle here. You know, they have different distances, but if I did a bunch of interactions, the average of all of those values, right, is going to be the mean free path. It's the average distance between the stuff in there. And the tau equals to 1 is when the mean free path is equivalent to the distance you've traveled, right? And it's also the transition from optically thin to optically thick. So if I say tau is much, much greater than 1, we call that optically thick. Another way to say it is it's opaque. You can't see through it. Okay? Tau of much, much less than 1 is optically thin. And that tau is wavelength dependent, right? Because you can have a plate of glass, which as far as visible light is concerned is optically thin, because you can see through it. Or you can have a plate of glass that infrared radiation is interacting with, and that's optically thick, because infrared radiation is contained by glass in the greenhouse.
What did you say was the mean free path?
The mean free path is equivalent to when tau is equal to 1. Okay? So tau equal to 1 is when the path length through the material is equivalent to the mean free path. Okay? All right. So and we do this, so in astronomy in particular, we put this in terms of tau because oftentimes we can't tease this out, right? The number density of a cloud of molecular gas. How big is it? What's x? We don't know, right? I mean, we know how big it looks on the sky, but we don't know how deep it is. And that's the important part. What about sigma? What's the cloud made out of? Well, maybe we could get at that. Maybe, if we have some spectroscopy, but we might not. It might be a dark cloud. The cloud itself is not emitting any light, and so it might be hard to tell exactly what the cloud's made out of. And the number density, so oftentimes those things are all just wrapped together into one variable called tau. Yeah?
Where do we define I naught? Is that we were right next to
Yep. Yeah. So if you're talking about if you've got an object here, right, I naught is the intensity before you enter the cloud, right? So that, well, before any absorption takes place. So if there's stuff right outside the source, then it has to be I naught at the surface.
But the intensity would diminish just because of vacuum distance.
Right, but you've got to, you can take that into account if you know the distance away, right?
Okay, so vacuum distance does not matter, it's just if there's...
Well, it does in the sense that you need to know how far away the object is in order to define what I naught. But this, you're raising another good point. Oftentimes we don't know what I naught is.
Okay.
Right? So what we're measuring, well, we have to make some assumptions. So let's say you have a cloud of molecular gas, and you're looking at a starlight traveling through it. You have to make some assumptions about the star you're looking at to figure out what I naught is. And then you'd have to know how far away that star is, right? Because if it was really close, then the amount of absorption you're getting to the material is going to be greater than if it was really, really far away and then hit that material, because then the material is not dimming it as much as the distance is. So you have to know the distance. That's what I'm saying.
So do we use only standard candles?
Yes. Well, we try to use only standard candles. And as we get when we get to the stellar astrophysics part of this class, you'll find out you can make almost any star a standard candle to within some uncertainty once you know some theory of star formation and stellar evolution. So we'll get to that. But what I wanted to talk about is what happens to the spectroscopic signature once we start to go from optically thin to optically thick. And I want to talk about an absorption line. We saw this with the absorption line in the planetarium the other day. If we have the intensity as a function of wavelength, or well, let's do the intensity as a function of wavelength, just because it's easier for me to think about it that way. Let's say you've got a continuous spectrum. It's a black body spectrum, looks like this. That's some source of light. You then put a gas in front of it that absorbs at exactly one frequency, or near one frequency. You're going to get an absorption line that looks like that, right? But the more stuff you have in front of it, the more absorption you're going to get. And the problem with absorption is what happens when you absorb so much that you're not getting any light from the center of that absorption line. What's going to happen next? I mean, you've absorbed all the light at exactly that point, but this has a shape. So what's going to happen to the shape of that thing? It's going to broaden out, right? So if you get something that's really optically thin, it might look like this, but something really optically thick might look like that, right? Some really deep feature, and this saturates, right? You can't tell anything more about that, so you have to be able to learn from the lines what's going on. And this shape, this evolution of the shape of this line from this point to this point is called the curve of growth. And studying the curve of growth in detail is kind of the subject of an entire course, right? Stellar spectroscopy, we could spend the whole time on it. I just want to write down that we're going to write down the graph that you get if you could measure the width of a line as you increase the opacity of the gas. So if you were to do an experiment where you had a star surrounded by a hydrogen gas and you just made the hydrogen gas denser and denser and denser and more absorptive, right? What would happen to that hydrogen line? And so the width of this thing, there's a mathematical definition, but it's basically the integral of, over the, we decide where the line is, and we take the integral under the curve of the continuum, which is this, all this, and then we subtract off the part that's just in the line. We normalize that by what's in the continuum, and you effectively get a width W of this line, and that width is getting bigger. So it's just a way of measuring the width of this thing. You write it down mathematically. The width of this is equal to the integral of the continuum line, which is just outside the line, minus the intensity of the line divided by the intensity of the continuum. So it's just a way of getting a ratio. And it's a number between, well, it's got to be a number between 0 and 1, right? Because you're dividing by the continuum. Yeah?
Just to make sure I have this earlier definition correct, if tau equals 1, that means the distance of the photon has to go through the barrier is equal to the mean free path of the photon through the particles.
Yeah, right.
Okay.
Yep. And I'm just going to draw this out, and this is all, we don't really derive this here. If you wanted to, you can go through and add in all the contributions you've read about in your book. What are the contributions to the lines? You've got the absorption, right? Then you've got all your Doppler broadening and all this kind of stuff. You can add all that stuff in, but this is really just the contribution to the absorption. And this means that the width as a function of tau has three pieces to it. One is the optically thin regime. Optically thin is when you're this little teeny tiny narrow line, and if you absorb a little bit more, the line just gets a little bit bigger, and you can see the full properties of the absorptive line in your spectrum. Okay? This rolls over when this saturates down. This line saturates, it gets bigger, whoosh, like this, gets bigger, whoosh, and then it saturates. Right where it saturates, this rolls over to a function that is proportional to the square root of tau. So it's just, or the square root of the log of tau. This is just very slight rise. This is proportional to tau itself down here. This is where the line is saturated, where it just begins to saturate. And this is, about tau equals 1 is when this starts to roll over. Right? At about tau equals 1, it starts to roll over. And then once you get to a very optically thick, so when we get into this regime, we wind up with the width suddenly accelerating its growth, because now you're growing in the line wings, and every time you grow in there, the width gets wider and wider. So this goes like this, whoosh, back up, and this is omega proportional to t to the 1/2. And that happens at about tau as 10 to the 5, or 10 to the 4. Okay, so that's the growth you get, and it tells you how a single gas will change depending on how much of the stuff you have. So you can look at a line width, right? If you can measure the line width, you can tell which part of the regime you're in. Are you an optically thick gas? Are you a transition gas, saturated? Or are you optically thin? And that you can see just from looking at a spectrum. So if I were to show you a spectrum of anything at this point without doing any calculations, you could tell me, is that a thin gas, optically thin gas, or optically thick gas, just by looking at it. So how do you know it's optically thick? Lines are saturated, big and wide. Okay? And the cool thing about that is that once you know that, that means just by looking at the spectrum, you know the product of these three numbers. So now as an astronomer, your job is to figure out how to tease those numbers apart. Do you know what the gas is made out of? If you do know what the gas is made out of, you know what that is. Do you know how far the distance is between you and the thing through the gas? Then you know what this is. And if you know those two things, you can figure out what that is. So you can get the number density, and you can get the composition, which is the cross-section, and you can get the size.
What's the most common things to know?
So commonly what you find out are the product of n and x, because you don't know how far through the gas it is, because it could be a light year, it could be 100,000 light years. And you know sigma. So you get sigma through, like, what is the spectral line that's doing the absorption. If it's a hydrogen line, then you know what this is. So you get the composition, let's say, from this, and then you usually know the product of n times x. And so oftentimes, by measuring this simple width, like if I were to take a spectrum and measure the width, I would know what tau is. I would know what line I was looking at, so I could tell what the stuff was. And then I could say, I am looking at a cloud of hydrogen gas that has a column density. In other words, the number of particles in a column of a certain area, which could be like, what typical column density, 10 to the 27 or something like that. So I could tell how much stuff, and then if I could figure out a way to know how big the gas was in X, tell you the size of the cloud. And oftentimes we'll look at the size of the cloud and say, well, it's roughly spherical. So if I know how wide it is, I know how deep it is. Which is not, that's not a bad, just to first order, that's not too bad. Okay? But the fun thing about astronomy, and the reason I got into astronomy and the reason I like it, is because it's all about what can you see and what can you deduce by just, without ever going there, just by thinking about it, really. Right? And you can start to make approximations and assumptions in astronomy, because an answer that's good to a factor of 2 is a good answer. This is what I want you to think about when you're doing your exam. I don't want 3.734528 times 10 to the 4. I want 6, not 1. Right? Because pi is 1, and pi squared is 10 in astronomy. So if you can estimate the size, let's say I'm looking at a gas cloud that's absorbing in hydrogen. I measure the optical depth, so I know how big tau is, and I know I'm looking at hydrogen, so I know what sigma is because I took nuclear physics or atomic physics, and so I know the product of n of x. How bad of an approximation could it be to say that the cloud is spherical? I might be off by a factor of 2, probably not off by a factor of 100. Pencils in space, it's probably a big blob of, so I might be off by a factor of 2. I can live with that.
But there are some nebulae that are like 1,000 times longer than that.
That's true.
You're looking down on those.
Yeah, that's true. But often, probably more of the cases you're looking at one that's, like you can't get sheets of gas, right? Because it could be compressed by a supernova. So you could easily get a sheet of gas that looks huge on the sky, right? But then usually you can, it's spherical and you can see where it's coming. But this is the thing, you get to use all these hints. But the thing I love about astronomy is that no one will ever fault you for assuming it's a sphere.
Yay.
No one will ever fault you for that. All right. Questions about optical density? So things you would want to know. And again, from the perspective of you are a physicist perhaps wanting to be an astronomer, or you want to be able to work on projects like this, or you want to be a programmer who does this kind of stuff, you don't have to remember any of this because, of course, you can look it up. But what you do need to remember is if an astronomer walks up to you and says, I really want to know what the composition of that cloud is, and I need to know its size and density, you're like, oh, I know what measurement to make, and I know I need to measure the width of the line. That's it. Measure the width of the absorption line, you got all that information. And then the astronomer is like, do that. Programmer, make that happen. Or you hire somebody because you're the liaison between the astronomer and the people who do the work. Right? That's called a manager. Right? You hire people who know how to, because honestly, this curve of growth stuff that I just slapped up here, that is, to do this for all known materials is 3 decades of work. I work with a woman called Linda. I can't remember Linda's last name. Linda Roth, who all she does is this. And she has done this for 47 years. And she is amazing because why? Because somebody has to know all that. Because I don't know it and I have to call up Linda and say, Linda, this is what I'm observing. I show her a spectrum and she's like, that's methane on Titan. I don't have to even label it. Right? Because she knows from the proximity of the different absorption lines. There's a guy by the name of George Wallerstein who did this for stars. I can give him 3 numbers, 3 wavelengths, and he can tell me what star we are looking at.
Like its actual...
If I give him the line widths of 3 specific, so I tell him, I say hydrogen alpha, beta, gamma, line width, blank, 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 and I give him some numbers. He's like, oh, that's delta Scoopy. The dude is insane. Like, he's been doing it. He's 87 years old. This is all he does. Right? Yeah?
So in your optical container, you didn't write what tau is.
Oh, it's just proportional to, it's linear. So the width is proportional to tau. As tau gets bigger, the width gets bigger. It's by the same proportion.
Width and tau proportionality.
Right, yeah, so this one should have been...
You did.
Yeah, I did. It was right there. Yeah.
Small.
We documented it on camera if you want to go back and roll tape.
Well, what I mean is a numerical tau proportionality.
Oh, I see. Yeah. So let's do it this way, right? This is tau equals 0. This is tau of about 1. This is tau of about 10 to the 4. Does that help?
What scale is that?
It's not linear.
All right.
Yeah.
Well, like 0 to 1 is about the same distance from 1 to...
Yeah, that's because that's the way I draw it. Yeah. Yeah, no, it's not. If you look, it's in your book, and it has, I think it's on a log scale. About 10 to the 4, yeah. 2 within a factor of 2. Right? Don't hold me to that. All right, I'm just going to write down, I want to talk about telescopes. So I just want to write down a couple of things, because we talked about continuous emission. right? Continuous emission is the most important thing in astronomy because it tells you the temperature. If I write down the intensity as a function of wavelength versus wavelength, I get a curve that looks like this for a continuous spectrum. What can you tell me from this peak? The lambda, what do you know from that lambda right there? Say it, what?
It's like medium.
Yeah, you know its temperature. And because I didn't write any scales on here, you don't know what the temperature is, but you would know that, is that one a hotter star or colder star? Hotter, because it's bluer, because wavelengths increase in this direction. Here's a cooler star, and here's you, right? Down here at about 300 Kelvin. That function is this, and your book goes through a nice derivation, which I really enjoyed reading, because every time I read it, I think a little bit harder about it, and I think I almost understand what's going on. So you might want to try doing it times. But the derivation, where this comes from, this equation, does anybody recognize this equation? It's called the Planck function. This comes from doing a statistical balance of all of the excitations and de-excitations of the atomic levels in a dense material, right? And it's dense because it doesn't have a chance to shoot photons out, so it's collisionally de-exciting, right? And this function comes from those assumptions using the statistical probabilities of those transitions. Now you can walk through the derivation about 7,000 times. I'm at 7,001 and I finally get it. So keep at it. But there's really no point in us going through here because I think we could do it together. You could do it another 6,999 times and then we'll come back and talk about it. Okay. But this does have some important things. One is this has a peak because we're combining two parts. We're combining this function here, which is diminishing, right, by wavelength. So that's this part. And we have this part here, which is increasing by wavelength. You put those two things together and you get a peak. And that peak is the thing that tells us the temperature. And there are two things that we know by looking at this. If you do the derivation, if I set this thing equal, if I take the derivative and set it equal to 0, I can find out where that peak is, right? And you find out that the temperature is proportional to 1 over lambda. The bigger lambda is, the lower the temperature. This is called Wien's law. The other thing, if you take this and integrate it from here to here, we get the total amount of flux that comes out of this thing, and that flux, which we call F, is equal to sigma t to the 4th, where sigma is the Stefan Boltzmann constant. And we all know sigma, 5.67 times 10 to the minus 8. Who doesn't know that? Right? Me. I know that because I just did a bunch of calculations with it. Okay? So this is the temperature. F is not force, this is flux. So what are the units of flux? Are watts per square meter. And that's because I have already integrated over wavelength, steradian, and hertz. Okay, so this is the flux coming out per square meter. If I have any glowing object, if I take a square meter, do you know, what is the surface area of a human? What's that? What would you guess the surface area of a human is?
Like average American or average European?
That's a good point. Well, if it's American, we can assume we're all spherical, right? Yeah. Oh, okay. No, well, assume you're a cylinder, right? You're 2 meters tall. I'm 2 meters tall. I'm about, yeah, something like that. I mean, if you were to do the estimate. So think like an astronomer. Assume a spherical cow, right? That's the... I have a thing on my board. Did you see that? It has a spherical cow and a vacuum cleaner, and it says assume a spherical cow and a vacuum. Nice. Anyway, so what we've done is we've entered, so about 2 square meters for a human, right? So if your flux, if you take 300 square or Q or 300 to the 4th, so 300 times 300 is what? 9,000? No, 90,000. 90,000 times 90,000 is what? 10 to the 4 times 10 to the 4 is 10 to the 8. It's like 10 to the 9, right? Order of magnitude, 10 to the 9. This is 5.67 times 10 to the minus 8. So 10 to the minus 8 times 10 to the 9 is 10. So you're putting out 10 watts per square meter. Now, if I'm not mistaken, I think a human surface area, if I did the calculation carefully, is about 6 meters. And I know that because you're putting out about 60 to 100 watts, depending on your temperature and your size. So you're all little 100-watt light bulbs. Right? So when next time you say, boy, he's not the brightest bulb in the you're really saying he's cold. That's all you're saying, right? You're not saying he's not smart. You're just saying he's cold. Okay. So this tells you the watts per square meter. So this is the exciting thing about astronomy. To get the luminosity, which is the important thing, this is the intrinsic power output in watts of an object, right? I need to take the area, assuming a spherical object, because we're mostly talking about stars and planets, and multiply it by sigma t to the fourth, and that's going to give me the power output. And I like this because this means if I can measure the temperature, is that easy or hard? It's super easy. What's its color, right? So this is easy. Measure its luminosity. Is that easy or hard? If I know how far away it is. Easy. Okay? So I know its size for a spherical object. Perfect. It's awesome, right? Now, the trick is we don't often know how far away it is. So we'll get to that later. We don't often know how far away it is. Okay, so that ends our discussion of light and the interaction of light and matter. We will use this when we talk about planets and stars from now on. So things I want you to really, really remember are how do you get the temperature from a wavelength? How do you get the flux from a temperature? And how do you get the luminosity and size from the temperature? How do all those things relate to each other? These are probably the most critical pieces of information. And this guy right here is the single most important equation in astronomy because it gives you a natural way to classify objects, because for the same size, a hot object will be brighter. Now, objects aren't all the same size, but if I were to plot, say, the stellar luminosity versus temperature, I should get to learn a lot about the properties of stars. And we're going to do that. And that's called the Hertzsprung-Russell diagram. Right? So that's why Hertzsprung-Russell, that's why it's not called the Hertzsprung diagram or the Russell diagram, because it's so easy, they both came up with it at the same time. It was like, oh, we just plot luminosity versus temperature. It makes perfect sense.
So why did you write power next to that equation?
Because luminosity is measured in watts. It's the power output, energy per second, coming out of the object.
Light power, right?
Well, what else is there?
Just the force.
Radium.
Okay, so there's the electromagnetic power, right? So yeah, so from an astronomy perspective, yeah, there's clearly, like, we could run a horse in a little buggy and put it on a wheel and get power. We have hydropower, but from when we're talking about light, when we're talking about radiation coming, this is integrated over the entire spectrum, not just visible. It's the whole thing.
Yeah, I forgot our conversation already.
Okay, did we document that? I can't. All right. Telescopes. Is this?
Yes.
Apparently. No. This is a trick question. I'm erasing this. Forget that. Seriously. Really important. Probably on your exam. Okay. Telescope. What is the single most important property of a telescope?
How well it gathers light.
How well it gathers light. And what is the single most important property of a telescope to gathering light? The aperture, the surface area, or the aperture of the telescope. The bigger the telescope, the better. So when you go to Walmart and it says you buy a telescope and it says 500,000 times magnification and it's this big around, you can do that. You just change the objective to get 500,000 times, but that's a crappy telescope because it doesn't collect any light. You can only magnify what you collect, right?
It's like they get those camera phones that say they got like 18 megapixels,
right.
And you're like, wow, all you got to do is make your JPEGs 200 magnification.
That's right, and then you've got it.
Wonderful looking quality.
So people always ask me why I went into astronomy. The reason I went into astronomy, one, the periodic table of the elements has 3 items. Hydrogen, helium, metals. The other one is this vastly simplifies optics. So all the optics you learned in 2220, forget everything about that. You hardly need to know any of it because everything you're looking at is at infinity. So all those problems we made you do when we say, we put an object at a lens at 10 centimeters from, and you got to figure it, no, you're at infinity. So if everything's at infinity, where does the stuff focus? At the focal point. Okay, so it makes the optics really, really easy. So, so if we have a lens like this, and everything's at infinity, that means every single line that comes through is going to get focused on the focus point, right? Another way to think about it is if you think about, so this all gets focused at a single point, but this is really not everything being focused here, because if you're off axis, you're still going to be collected provided you're in the field of view, right? So we use a slightly different way of drawing this. I'll use a different color where we imagine a star, let's say here. If the light from the star goes through the center of the lens, what happens to the path? Remembering from your optics, it just keeps going, right? And same with this one, through the center of the lens, just keeps going. There's a focal plane where if I were to set something like a camera or a detector, I would get a star field, right? And that's called the focal plane. Focal plane, and the focal plane is at the focal length, f. And your book uses big F, so I'm going to do that. And there's an angular separation between those two stars that you can measure, and if you know the geometry of your telescope, you can relate that to what's called the plate scale, right? Now, any photographers in here? Okay, so what's an F number? What, like when they say F8, what does that mean? I have a hard time remembering too, so nobody knows this anymore because you just hit the auto on the photography thing and go to town. It's called the focal ratio, right? Yeah, yeah, so it's kind of a trick question because it's a really silly way to do this, because F8, right, is the ratio of the focal distance to the diameter of the lens, right, means that ratio is 8. So you look at this, and every time I look at this, I'm like, I have to think about it, because F8 looks like the ratio should be 1/8 or something. But F8 means the ratio of the focal length to the diameter is a factor of 8. So if we imagine, this is kind of crazy about complex optical devices, because like that camera over there, which doesn't exist, F8, what does that mean? Well, what's the size of the aperture of that camera? Is like 3 centimeters, maybe? Yeah. So we take the diameter, 3 centimeters, let's say. Well, let's make it easy, 4 centimeters. So what's the focal length at F8? .32. So wait a second, you're trying to tell me that the focal length of that lens is 32 centimeters? It's like that. What? See, the astronomer in me like, but all telescopes are just tubes with a lens at the end of it. But what's happened in that camera? They have lots of lenses, a lot more optics. They've folded the optical path to make it compact. But if you go back and look at the original cameras, what did they have? Those really old school cameras, whoop, right? The lens, they had to put it out, and they had to make it 32 centimeters long to get an F8. But now we've got all these cool optics that fold back. But telescopes, we usually don't do a lot of complex optics until we get to the big stuff, right? So really, we're saying, if this is the case, the diameter of this would be 1/8 the length of this. So that would look like, to scale, something like that. There's our focal length.
F over D, what is that called again?
This is called the focal, the F ratio, the focal ratio. It's and so when you see something that says F8, now you're going to have a lot of fun with your camera now, because so what's going on? What are you changing when I change the F ratio? This is interesting, especially photographers. So I take that camera, and I can, right now it's on auto, I can set it to whatever I want. Set my camera to, I take the little knob, and I rotate it to F16, or wherever you do it on the, probably on the computer thing now. It's probably not a little knob anymore. But the f-stop used to be a little knob, so I change it to F16. What did I do? Change this to 16, right? So F, did I change F? No, so what did I do to D? Decreased it by a factor of 2. So I decreased the aperture area, the aperture diameter by a factor of 2. which means I'm letting less light in. And why would I want to do that?
It's too bright outside.
It's too bright outside, right? So you can decrease the exposure length. That's another way to affect that. But maybe you don't want to decrease the exposure length for some reason. Maybe you're trying to do like the cool water thing. Yeah, where you want to leave a long exposure time, but it's really bright out. So you stop it down a bunch so that you let in less light through the aperture. Now with telescopes, you don't ever want to do that. In fact, you want, well, so what are the properties of a telescope that you're really interested in? The properties of the telescope is you want the diameter to be as large as possible, and you want the focal length to be as short as possible. Because if I take a lens with a fixed focal length and just make it bigger, right, what's going to happen to the, well, so, oh, sorry. If I just make a lens bigger of the same curvature, what's going to happen to the focal length? It gets pushed out, right? So if I take a lens this big, like there, it's this big. But if I make it this big, now it's this huge long tube. And if you make it the size of a nice big lens, you're talking about something that's 120 feet long. And that's a little unwieldy, especially if you've got a big lens on the end. So you could make the lens have a bigger curvature, but that's going to be a problem because glass doesn't transmit the same wavelengths the same. You get something called chromatic aberration. You get little rainbows, which you don't really want most of the time. And so that you can't just make the curvature of the lens, so oftentimes you fold the optics, right? So instead of going out for 120 feet, you put a mirror here, right? And then you come back here and put another mirror, and then do that. But then you've got this thing in your optical path, and that takes up some of your area. So it's tricky to build large telescopes, at least with lenses. Okay. I want to briefly write down the plate scale because that's going to be important if you want to figure out what size detector to put here and how big it can be. It's called a plate scale because we used to put photographic plates. And if you ever go down to, say, Flagstaff, they've got the Lowell's Original Observatory, right? They still have the plate holder. And they made the plates really big, right? Because they wanted to get as big a field of view as possible. And they take these photographic plates, glass plates that had silver oxide on them, right? I think it's silver oxide, isn't that what they used to put in film emulsion? I don't know, anyway. What kind of photographer are you? Are you a camera or something? Anyway, so they call it the plate scale. But the plate scale, you can relate this angle, theta, which is how far things would be separated on the scale, to, if this is the separation on the plate or on the camera, we'll call that D. Just work out, that's just a triangle there. And let's do, if presuming these lines are very, very close together, I can use the small angle approximation. And the small angle approximation says this is approximately d over f, because it would be the tangent if I took the angle. And if we write that, that's in radians. And if we write that in terms of arc seconds, just doing the conversion, the angle in arc seconds is equal to 206.265. That's the conversion of radians to arc seconds times d over f. And I just wrote that down because that allows you to figure out how your focal length is going to impact your field of view for a given size detector. Arc seconds, yeah. Maybe I should do this instead. Your book has of units arc second. So for a fixed focal length, right, if I make my detector bigger, I get a bigger field of view. Right? This is the name of the game for astronomy right now. They call it paving the focal plane in silicon, right? Because you've got this huge telescope. So the focal length in principle is not small, right? Oftentimes the focal length is pretty large because you've made this huge, and you can only bend, even if you're using a mirror, you can only bend that light so much, right? So the focal length in principle tends to be pretty long. So if you want to get a large field of view, you need to make D, the size of your detector, huge. And you've seen CCD cameras, right? And they're not that big. Like a really high quality CCD chip is this big, CMOS chip or something like that. So what they do is they take those and they just put thousands of them on these big detectors, and they just pave the plate with silicon chips to get the biggest field of view possible. And that's a way of accommodating that. You don't have to change you can make a big, huge telescope. You don't have to curve the light too much, and you just make a really big optical surface for the light to interact with. All right. So you all want to go out and buy telescopes? Yeah?
I do want to, but I don't have the money.
Yeah, you do have the money. Because I'm here to tell you. What's that?
We were saying giving it.
No, I'm here to tell you that the best thing you could do, there's an $8 binocular. And maybe you don't have that kind of money either. But you soon will. You will eventually graduate and get a job. A real job. A real job. You'll have a bigger real job.
Yay.
Like mine, where I get to buy whatever the heck I want whenever I want it. As long as I want, yes, as long as I want small things, like supercomputers. No, you can buy a nice pair of binoculars, and that's pretty good because one of the calculations you're going to do, I think you do it on your homework, if not, it's done in your book. You can calculate out that the largest telescope you need to see resolution that's good enough through the atmosphere is about this big, right? It's about 10 centimeters. That's not bad. So if you get a nice pair of binoculars, that's pretty much the resolution you're going to get, no matter how big your telescope is. Now, the only thing you gain by getting a bigger telescope is you can collect more light. You can see fainter things, but you'll see them faint at the same resolution. If you can make your telescope bigger and maybe get it in space, then you can see a much finer resolution, right? But
you use software now to correct for the interference.
Right. So there is this technique called adaptive optics, where what they do is they either use usually they shine a laser beam up that bounces off of the atmosphere, and then they use that. They watch the laser beam reflection kind of bounce around because of the scintillation in the atmosphere, and then they say, oh, they send that, they through software figure out what that motion is, and then they actuate usually the secondary mirror to compensate. But some of the new telescopes even have actuators on the primary mirror, and they dynamically flex the instrument to keep it accommodating for the atmospheric disturbance. And in fact, the new instrument they're talking about building, called the Overwhelmingly Large Telescope, the OWL, right, is going to have a dynamic surface, 30 meters in diameter. And they claim once we learn how to do that, what's that?
What's wavelength?
It's going to be visible wavelengths. And the guy who's building it claims that once we get this done, we won't bother with space telescopes anymore.
What organization's building this?
It's a private consortium. I think University of Arizona is making the mirror segments. I haven't started building anything yet, but yeah, the Overwhelmingly Large Telescope. Yeah, it's usually so Caltech has a big share in it. A bunch of other private universities do. Now that's in contrast. So the Keck telescopes, did I show you pictures of Keck last time? Maybe I just did my astronomy. Anyway, the Keck telescopes, they're 10 meter in size. There's 2 of them, and they are privately run. So if you want to use them, you need to get a job at Caltech, or get a collaboration with somebody at Caltech. That's not the same for the European Space Agency telescopes in the southern hemisphere. I can propose to those and go use them whenever I want. And Hubble Space Telescope belongs to you, right? You paid for it. If you go to Hubble Space Telescope and download all their images, provided you credit Hubble Space Telescope, you can do whatever you want with those images. You want to make coffee mugs, do whatever you want. They're public domain images because they were paid for by public tax dollars. So, although why you'd want a coffee mug. Actually, I had a coffee mug once. It was cool. You put hot coffee in it, and it showed the infrared Milky Way, and when you drank the coffee down, it would go back to the visible. It was awesome. All right. Okay, so the last thing I want to talk about before we finish today is detecting photons, detecting light, and some of the issues that come up with detecting photons, because that's what these cameras do. I don't want to get into the statistics of this because how many people have taken a statistics class? Okay, you've heard of Poisson statistics? Maybe you did. Was that in your statistics class today? Yeah.
In high school, not here.
Right. Yeah. So it's if you're counting something, and it depends on what the something is, but photons are one of these things. It's a statistical probability distribution. Like if you count the number of photons coming in, there's some actual number of photons, and then there's what you can count. And there's when you count the photons, you're really just counting a representation of what's really there. And so you can get a distribution of what those counts should be, which means every time you count photons, there's some uncertainty associated with counting the photons. Now, I think this is also true for presidential elections. As far as I'm concerned, you can say you can count every vote, but you can't, because you're just taking a sampling by trying to count the votes. I think I don't know if they're Poisson distributed, but they're distributed by something. So in Poisson statistics, the uncertainty squared is equal to the number of photons counted. So this is the uncertainty, and this is the number of photons counted. And so what you would to write this down, let's say you count 100 photons, right? You count 100 photons. Well, the uncertainty in that is going to be the square root. So if you count 100 photons, you can only know that number to plus or minus 10. So my rule for presidential elections would be this. If the difference between the two candidates is less than the square root of the total number of votes, we do the election again. Does that seem reasonable? I don't think it would be, because if you've got, how many people vote in an election? It's like 10 million. Yeah, about 10 million people, something. Or no, 100 million people. 100 million people, what's the square root of 100 million?
There's no way 100 million people vote.
No, that's true. It must be 10 million. Let's say 10 million.
I would guess 40.
Let's say 40 million.
Let's do 40.
Let's do 100 million, because that's an easier number to take the square root of. Okay. Well, let's do so 40 million is 4 times 10 to the 8th. No, that's 400 million. 10 to the 7th. See, that's hard to take the square root of. So let's do 10 to the 8th. 100 million, just because it makes the math easier. What's the square root of that number? 10 to the 4, right? So it's 10,000. If a presidential election is ever called to less than 10,000 votes, we do it over. That's my rule. Okay.
I think presidential elections are only Poisson distributed if Poisson had some sort of monetary aspect.
Yes, exactly. Yeah, I don't think they are. But the point is, if you measure this, there's some uncertainty. And even if there's no other uncertainty in your instrument, this is the important thing. There's no random error in your detection. There's no systematic bias, nothing. There's still an uncertainty in just the counting of the photons.
Is this a proportionality or an actual?
This is an actual equals, right? So if there's 10,000 photons, you have to say plus or minus 100, right? And the more photons you count, the bigger the uncertainty, but it goes like the square root of that. So we can write down the signal to noise. The signal to noise is equal to the signal, which is mu, divided by the noise, which is sigma. So the signal to noise is mu over mu to the 1/2. Did we do that right? Which is equal to mu to the 1/2. So the signal to noise is a fractional value. Well, it's not a fractional value. It's a value which is proportional to the amount of photons you're collecting. So if you are collecting 100 photons, your signal to noise is 10. And this is important because what do we call a detection? Is a signal to noise ratio of 1 a detection?
No.
How about 2? So here's your signal. Here's your noise. Right? The scatter in that, and then there's your detection. Is that a detection? Signal to noise of 2. Sketchy, right? Right. If you're just trying to say, hey, I think we might have found something, you should give me money to build a new telescope to see if we've actually found it, this is fine. But if you're trying to say, I have conclusively detected something, no. Typically a signal to noise of, well, what is a Large Hadron Collider? There's like 5, right? No, it's not that high. I think they have a 5 sigma, which is a signal to noise of 5. So when we say 5 sigma, what we're saying is, if this is your noise, you want to be 5 times larger than that. So 50 would be your detection, right? So, but with photons, it's all correlated with this. So if you want a signal to noise of 10, you have to collect 100 photons.
How about
Maybe there's some rule they have, like they have to have a chance of error in their measurement of.
Well, yeah, yes, and that's because we've got to include more error sources. We have this is just the counting of the photons.
Oh,
okay. So, what other sources can we have? Well, just talking about sources of noise from photon counting, you're not just viewing a star. You're viewing a star against a background of ambient light, right? And so we really want to say, well, the total uncertainty is going to be equal to the uncertainty from our source plus the uncertainty from the background. And I'm collecting photons from the background. They're scattered from other stars. They're scattered in the atmosphere. Maybe they're caused by light pollution. And so that means that the signal to noise with a background, this is called a background limited source, which means if it's not brighter than the background, you're not going to see it. Background limited source. The signal to noise ratio is going to be the signal, which is the number of photons you get from the source, divided by this guy, sigma s squared plus sigma b squared to the 1/2. Because it's just the total sigma. But this is proportional to the sigma squared is proportional to the number of photons from the source, and sigma squared is proportional to the number of photons from the background. So I can write this as sigma s divided by sigma s plus sigma b to the 1/2. But hopefully, if you're doing your astronomy right, the source is much brighter than the background. Would you agree with that?
Yes.
Yeah. Wait, why didn't that come out? For sigma b greater than sigma s. Why did that come out that way? Where's my stop recording? No, because the background, oh, right, okay, yeah, I get it. Yeah, this is important. So you're looking at your source here, right? But what's your telescope looking at? All of the light in its path, and you have this little star, right? So if you add up all of the photons from the background, that's really more than your source. Not in the direction right to your source, but in your telescope it's more than your source. So your background photons are going to be greater than your source if it's background limited. So we just set this equal to, we ignore mu sub s, and this just becomes mu sub s over mu sub b to the 1/2. And that's called a background limited source. That means that you've got a ton of background from the sky, and you're looking at this little teeny tiny star. Right? And that's always how it goes, right? Well, so in the laboratory, you're often not background limited because you can put up big shades and make sure you get no ambient light and you just have your source, in which case you could ignore the background. No, you can't. Well, you kind of can. Like you can make sure your telescope is baffled, so the person who turns on the flashlight in the parking lot, you don't get that, but you still have the background from the sky. All right, so this is a background limited source, which means if this is going to dominate over the number of photons from our background are going to dominate over the number of photons from our source and reduce our signal to noise. Okay. So how are we doing on time here? All right, I want to do something. We got 5 minutes. Questions on signal to noise? What's the name of the game?
Telescopes.
Telescopes, you want more signal, less noise, right? But this kind of raises a point, right? So what, if you could design a perfect telescope, well, let me write this down, okay? I'm going to write down, let's see, how can I do this? Yeah, let's go ahead and do this. So let's look at the number of photons per second you get from a source. And let's see if we can game the system a little bit to make it easy for us. The number of photons you get for a source is going to be equal to the energy per photon divided into the flux at that wavelength. So if this is the flux at that wavelength, if I divide that by the energy of photons, hc over lambda, divide that, that's going to give me the total number of photons, right? Because I've got energy divided by the energy per photon. That should give me the total number of photons times some bandwidth times the area area of my telescope, the diameter, the fraction of light that gets through the atmosphere, times the fraction of the telescope, times the quantum efficiency of my detector. So at every point, this is the energy that's coming from the source. And then I have the amount of energy in that wavelength band. So if I make really broad bandwidth, I get more signal, right? If I have a big telescope, I get more signal. My atmosphere, if I can get rid of my atmosphere, because this is the fraction of light that gets through the atmosphere, if that's 1, that's perfect, right? So this is the contribution due to the atmosphere, ATM. My telescope has optics in it. Can I make perfectly transparent optics? No, but I could try. So I have to control that. And then my detector, every photon that hits it, will every photon turn into a signal I can detect? No. So this is the detector. It's called the quantum efficiency, or the QE. So that's the source. That's a cursive Q, yeah, for quantum efficiency. That's the source. Well, I can write down the same for the background, just to make this easy. Background is going to be, again, the energy per the background source, number of photons. I take the background, the background flux and divide it by the energy per wavelength. There's the fraction of sky I'm looking at, right? If I'm looking at the whole sky, whole steradian of sky, am I going to get a lot of background? Yeah, I want to make that as small as possible. Yeah, no. I get my, again, wavelength stays in there. The area of the telescope doesn't change. That's the same. The atmospheric contribution doesn't change. The telescope contribution doesn't change. And the quantum efficiency doesn't change. So just looking at this, the total number of photons I get, sigma s, is going to be ns dot times t, the amount of exposure time. And the total number of background photons I get is going to be nb dot times t. So if I integrate for longer, I collect photons from all of these things. Yes? Those phi's are, no, they're a fraction of the light that makes it through the atmosphere or the telescope. So they're a number between 0 and 1. So if all the light gets through the atmosphere, so if I'm observing on the moon, theta A is 1. If I'm observing in this crud in Ogden, Utah, theta A is 0. And I should just stop what I'm doing because there's no point. Right? Right now is bad times astronomy. Yeah, Nate, did you? This is background flux. This is background flux. This is source flux. And I know. But your book uses those, so that's what I'm sticking with. So, question?
QM with the HC.
What the? HC, this is the energy. So I'm taking the flux per wavelength and dividing it by the energy per photon. That's giving me the number of photons. And since this is a flux, it's a number per unit time. Okay? So the only reason I'm putting all this up here is because you can see where we can start to compete. Now if I make the telescope bigger, right, that's going to adjust the A. Because if the telescope's bigger, that's going to adjust the theta. That's going to adjust the area that I'm seeing of source. So the bigger the telescope, not only does D get bigger, but theta gets smaller. So that's good. Big telescope gives you more source, less background. Yeah?
Can you explain again about pi theta squared?
This is the area of the sky that your telescope looks at. So the bigger that area is, the more background you get. So I want to just throw all these together in ratio from this thing. If I write down my signal to noise, my background signal to noise, just write this up again, is just sigma or mu s over mu b to the 1/2. And that's going to mean, using those things over there, it's just ns dot t divided by nb dot t to the 1/2. And that's proportional. If you work all that out, do the ratios, drop out the constants that don't matter, this is equal to f lambda d over theta phi A times lambda phi t q over s lambda to the 1/2 times t to the 1/2. That's just the ratio of those two quantities. And I say proportional because I dropped a bunch of things that don't matter. But let's look at what does matter. What matters is, how can I increase my signal to noise? You tell me. What's the biggest, how can I get the biggest signal to noise possible?
Put it in space.
Put it in space. Send this to 1, right? Put the biggest what and put what into space? The biggest telescope possible. D should be as big as possible. Look at the brightest object possible. Often you don't have a choice. You're just looking at what you're looking at. Make sure that your field of view is as small as possible for the source you're looking at. Right? So you have as little background as possible. And then it gets a little bit interesting here because now these things are just linear. These are to the square root. So if I increase my bandwidth, use a broader band filter, right? I can increase my signal to noise. If I can reduce my background flux, like maybe move out of Ogden and go to Eden Valley, so I don't have a lot of scattered light. If I can increase my quantum efficiency and telescope throughput, those are okay too, but they're not as important as these, right? And typically, you have access to the telescope and the skies you have, right? I'm in Ogden, I've got an 8-inch telescope, and I'm at Weber State University. I can't do anything about this, or this. But what I can do, and I can't do anything about this, or this, or this. So if I'm limited to, somebody just gives me a telescope, what's the only thing I can do? Look at bright things or look at them for longer, right? So you can integrate for longer, you can look at things that are brighter.
So to get the best noise ratio, we should take the Hubble telescope and put it in a very tiny spot on the sun.
Yes. That would be awesome. Except unless, it depends on what your source is, because if your source is this part of the sun and you're looking at this part, then your signal to noise goes back to junk anyway. No, but it's an important point. Like the whole purpose now, and the reason I wanted to bring this up now is because there may be people in here who are taking astrophysics because it was the next course available to you in your sequence, right? But if you end up being an engineer for astronomical telescopes, an applied physics degree is perfect because you can figure out how to manipulate all of these things. And frankly, that's what we're doing. Whenever we design an instrument, we're just saying, well, what can we do? What do we have control over and what don't we? The quantum efficiency for CCD cameras is pretty much fixed now. It's about 99%. We're not going to improve that. All right, we're out of time. I apologize for going a little bit over.